Welcome back, everyone. We didn't say it at the end of the last segment, but that was the end of differential calculus. We are done with differential calculus. And if you had been taking this class a few generations ago, that would have taken us the whole semester. But we've made some progress then. You're a little bit smarter than your ancestors were. And so now instead of differential calculus taking a full semester, and integral calculus taking a full semester, and then series and differential equations taking a full semester, we combine those 3 semesters all into 2. So we're done with differential calculus, and what we were doing there, in every case really, you might not have realized this, we were given some quantity and we were finding the rate of change. Whether we were finding the slope of a curve, whether we were doing a local linearization, even those optimization problems like we did last time. That's really what we were doing. We were trying to find in those cases where the rate of change was 0. Now, we're going to turn to integral calculus and the inverse problem. So about half the problems in life, you're given a quantity and you want to find the rate of change, and the other half are exactly the opposite way around. You're given a rate of change, and we like to go backwards and try to find out what we can say about the quantity itself. So you might remember that we started this semester when we did differential calculus by, we knew an object's position, and we wanted to find out its velocity. Now we can try to answer the inverse question where we're given a velocity function, try to figure out something about the object's position or how far it traveled. So differential calculus, the word came from finding differences. The rate of change is one difference over another difference. Integral calculus is going to be about integrating things, which means putting things together. And I hope that will become clear as we do some examples. So we're going to start from a very basic example, just like we did with differential calculus. We've got oil leaking from a tank at a decreasing rate, which we're calling f of t, liters per hour. And we just have some data. We don't actually have a formula for the function. This is all that we have. Given these rates of change, we'd like to give the best possible overestimate and the best possible underestimate for the amount of oil that actually leaked out during these 12 hours. And we're starting from scratch now. So if you were feeling a little bit overwhelmed by some of those family of curve problems last week, now we're starting brand new and we're more easy stuff here. So let's look at the first 3 hours. In the first 3 hours, what's the greatest number of liters that could possibly have leaked out? What do you think that would be? We know that the rate was decreasing. So that rate started at 25 liters per hour and went down to 22 liters per hour. If it had stayed 25 liters per hour the entire time, how many gallons would have leaked out? 75 gallons. Because if we go 25 liters per gallon for 3 hours, we would get a total of 75 gallons. So I'm going to write this right here, what we just did there, 25 times 3. And then up above, let's write symbolically what that was. We took f of 0, and we multiplied by this change in time. And do you remember what we write for change in? We write that Greek letter capital delta. So this is saying f of 0 delta t. So this is, and I'm going to write something else up here in a minute. This is telling us the greatest number of gallons that could possibly have leaked out in the liters that could possibly have leaked out in the first 3 hours. Now what about the next 3 hours? From time 3 to time 6, the rate was never more than 22 liters per hour. So the greatest number of gallons that could possibly have leaked out would be 22 liters an hour. Boy, I'm trying to change to liters for our very worldwide audience here after doing this problem with gallons for years. So that's why I keep saying gallons. If it had been 22 liters per hour for 3 full hours, 66 gallons would have leaked out. So there we would have done 22 liters per hour times 3. So that was f of 3 times delta t. And we just keep going. So in the next interval from 6 to 9, the greatest rate was 18 liters per hour. So if we had gone 18 liters per hour for 3 hours, that's how many would have leaked out. So that would have been f of 6 times delta t. And in the final interval of 3 hours, the rate was never more than 16 liters per hour. So the most that could have possibly leaked out there would be 48 liters if we had really stayed at 16 liters per hour for all 3 hours. And you'll notice that we never use this 15 because that is not the greatest rate in any of our little subintervals here. If we were going one more interval, we would end up using that, but we haven't used that. So I think when we add this all up, we get 243 liters. And now let's decide what we want to put here. What this is, and we'll talk more about these later in another segment, these are called Riemann sums. And in particular, this Riemann sum, every time we were given a choice between 2 values, we always chose the value on the left. So this is called a left-hand sum, which we abbreviate LHS, and in this case of 4, because 4 was the number of subintervals that we used. So we say LHS of 4. That stands for left-hand sum. Now you should ask yourself, and we'll answer this question later, but you can start thinking about it, is the left-hand sum always going to give an overestimate? Or is there some times when the left-hand sum will give an underestimate? Now let's try to do our underestimate. So in the first 3 hours, what is the smallest number of liters that could possibly have leaked out? We know that the rate was never more than 22 liters per hour. And again, this is because the rate is decreasing. So we know that the rate didn't go from 25, maybe up to 29, and then down to 11. The rate went from 25 down to 22, decreasing all the way. If the rate had only been 22 gallons an hour for 22 liters an hour for 3 hours, how many would have leaked out? We would have said 22 times 3, or 66. And what did we do there? That was f of 3 times delta t. So as you can probably guess, this is going to be the left-hand sum, because in each case, we're going to choose the right-hand sum, because in each case, we're going to be choosing the value on the right. In the next interval, from time 3 to time 6, the smallest rate was 18, the value on the right. So we'll say 18 liters per hour for 3 hours. So that was f of 6 delta t. And then the pattern is just going to keep continuing like this. When we have the choice between the 18 and the 16, we'll choose the 16, the value on the right. When we have the choice between 16 and 15, we'll choose the 15, the value on the right. So that will go like this. We'll say f of 9 delta t and f of 12 delta t. So that gives us 16 times 3 and 15 times 3. So here it wouldn't actually be too much trouble to add these up because we only had 4 terms. But imagine that you had 400 terms if you were trying to use much smaller intervals, or you're writing some computer program to do this. Notice that most of these terms already appeared in the left-hand sum. So if we've already added up the left-hand sum as we've done here, and this will come in handy later on, how can we get from the left-hand sum to the right-hand sum by doing the least amount of work? Both sums had a 22 times 3, they both had an 18 times 3, and they both had a 16 times 3. So all we really did here was we replaced a 25 times 3 with a 15 times 3, meaning that we should have gone down by a total of 10 liters, so 213 liters. Right. So this is the left-hand sum, this is the right-hand sum. So here they're 30 liters apart. And you might be happy with that, or you might say, I wish I'd been able to get them closer together. How often would I have needed to do? How often would we have needed to measure these to get these sums to, say, within 3 liters of one another? So that's our next question. How often would we have needed to measure this rate in order to get the estimates within 3 liters of one another instead of within 30 liters of one another as they were up here? So that means what we want is we want the difference between the right-hand sum and the left-hand sum. And I'm putting them in absolute values here because that's the standard way to do it. We don't know which one is going to be necessarily the bigger. I mean, in this case, of course, we do know that the left-hand sum is the bigger of the two, but this is a more general way of looking at that. We want the difference between them to be less than 3 gallons, or I guess within, probably we can say less than or equal to 3 gallons. 3 liters. 3 liters. So what's going to happen when we subtract the left-hand sum from the right-hand sum? This is why we made this comment before that most of the terms cancel. The term that's going to be in the right-hand sum that's not going to be in the left-hand sum is going to be f of what? That's going to be the f of 12 times the delta t. That's the only term that was in the right-hand sum that wasn't in the left-hand sum. And what was the only term that was in the left-hand sum that wasn't in the right-hand sum? That was the f of 0 term. And remember, we don't know what this delta t is. We're going to change the delta t. We're going to make it smaller so that this answer ends up being less than or equal to 3. Well, what is f of 12? F of 12, we know, is 15. And f of 0, we know, was 25. So this just gives us negative 10 delta t. And when we put the absolute values in, that's 10 delta t. So we have 10 delta t less than or equal to 3. Remember, delta t is the width of each one of our intervals. So that means delta t must be less than or equal to 0.3 hours. So 0.3 hours, I think, is 18 minutes. So we would measure, if we measured the rate every 18 minutes, or every 0.3 hours, we're guaranteed to get estimates within 3 liters of each other. And let's pause and think about this for a second. We're going to make up, when we measure them every 18 minutes instead, we're going to get some whole bunch of new numbers in this table up there. We don't know what they're going to be. Like the value at 18 minutes, at f of 0.3 and f of 0.6 and f of 0.9. We don't know what any of those numbers are going to be. And yet we know that when we take the right-hand sum minus the left-hand sum, they're going to cancel no matter what, and we're going to get the estimates within 3 liters of one another, just as we want. So I hope this reminds you a little bit of how we started out with differential calculus, where we were trying to find the instantaneous rate of change, and we first looked at average rate of change. That is the average rate of change over some finite interval. That's sort of like what we're doing here, these delta t's. Of course, we eventually want to be able to get a more exact answer, and so you can start to think back to what we did to get an exact answer for the instantaneous rate of change and what process, important calculus process we needed to use there. That's the same process that we're going to end up using in integral calculus. But right now we have a check your understanding on this particular idea, so please give that a try.